Testing 1, 2, 3. Okay, it's working. Yay. All right, folks, we're going to be on page 86. 86. And before we go into letting Tyler, here, we'll turn this on again so I'm a little bit louder. Before we get into Tyler telling us all the stuff, we are going to take a look at this atom here on the left, and we're going to take a look at the atom on the right. We have one of them has 5 protons and 5 neutrons. So we have a 5 and a 5. 5 protons, 5 neutrons. The one on the right has 5 protons and 6 neutrons. So, for each of these, what would be the mass number? Do you remember how to find mass number? Here's fine. Mass number equals something plus something. Protons, because protons have a mass of how much? Protons have a mass of 1. What's the unit? Atomic mass units, AMU. And the neutrons are the other ones that have mass. What is the mass of a neutron? Also 1 AMU. Okay, so the mass number is the protons plus the neutrons. So, what is our mass number for the atom on the left? Page 86. I'm going to call a name. I'm going to draw a card, because you guys can all do this. Okay? So have a chat with your neighbor and decide, what is the mass number for this atom here? Yana. 10. 5 plus 5 equals 10. So it weighs 10 what? AMU. AMU. And what does AMU stand for? Atomic mass units. Next question. You'll need your periodic table for this one, so if you don't have your yellow periodic table out, get your yellow periodic table out. And periodic table. Go look on your periodic table and decide which element is this. And how do you know? What do you have to look up? Yes. Yeah, you look up the atomic number. Who has an atomic number of, is it 10 or is it 5? Protons is the atomic number. So who has an atomic number of 5? Boron, okay? Okay, so that's our atomic number there. It has 5 protons, so it is boron. Do you remember how to say this is a boron atom with a mass of 10? What would we do to the name boron to say that it has a mass of 10? Sorry? We put a dash, and then we write 10. That number there, what do we call that number? That's the mass number. We are on page 86, 86. How would we do this if we wanted to write the element symbol instead? Where would we put the 10? Yes. On the left side at the top. So the mass number goes up here. What goes on the bottom? What number goes down here? That's our atomic number, yeah. So the atomic number goes down there, and so that's going to be a 5. Okay. So that is our element that we have so far. Let's go over to our other atom on the other side of the page. What element do we have? Chan, what element do we have here? We have boron because, again, it has 5 protons. So we have boron. And what is the mass number of this boron atom? It's 11. It's 5 plus 6 equals 11. Where would we put that 11 in the name of boron? Murtaza, where would we put the 11 in the name for boron? Yeah, we'd put it over here with a dash and then an 11. Remember, that is the mass number. How do we find the mass number? It's equal to the what plus what? Protons. And what things have mass? Protons have mass. Neutrons have mass. And it's not that electrons don't have mass, but their mass is way too tiny, too small to matter, okay? So the mass number is the protons plus the neutrons. Okay, how would we write the symbol for this? We would put B. And where does the 11 go, Ben? Where does the 11 go on the symbol? Yeah, top left, absolutely. Okay, so there's our 11. And what goes down at the bottom left, Hannah? The 5s, because that's our atomic number. Okay, so we have 2 versions of boron. We have boron 10 and boron 11. What is the name that we give to 2 versions of the same element? Different versions of an element are called isotopes. Yes. What do isotopes have that is the same? They have the same protons, but different Is it electrons or is it neutrons? What's different about our isotopes? Different neutrons. And if the neutrons are different, what else is different? Different mass number, yeah. Okay, and we can fill in the rest of these boxes here. Our boron 11 weighs 11 AMU. And then finally, our boxes down here, we have one. What are the things that weigh one? Proton. Or one. What's the other thing that weighs one? Neutron. Weighs 1 AMU. So protons and neutrons weigh 1 AMU. Electrons weigh close to 0. So the mass number is the mass of a specific isotope. All right, so I would have to give you the number of neutrons for you to figure out the mass number. There is no way, there's no information on the periodic table that lets you know the number of neutrons. There is no information on the periodic table that gives you the mass number. So I would have to give you the mass number if I asked you to find the number of neutrons. So if I don't give you the mass number, you cannot find the number of neutrons. There's nothing on the periodic table that tells you the mass number. The mass number is not on the periodic table. You can find it written in either the name or the symbol. So I might say to you, you have P32, and that is your mass number. But I'd have to tell you that. I might say you have phosphorus 32, but I would have to write that 32 for you. By the way, if you have phosphorus 32, how many neutrons, let's start with this. How many protons in phosphorus 32? Go check on your periodic table. How many protons in phosphorus 32? Yeah, P. There's phosphorus. Whoop, where did it go? There's phosphorus. What number tells you the number of protons? 1, 5. That's your atomic number. That's the number of protons. So it is 15. So we have 15 protons. How many neutrons? In phosphorus 32. Yeah. How would we figure out that there's 17? What we would do is we would say that protons plus neutrons has to equal 32, the mass, right? The mass number. And so, in order to find the neutrons is going to be equal to 32 minus the protons, which is going to be 32 minus 15, which gives us 17. And if you happen to be using this notation here, this isotope notation, the 32 would go at the top. What would go at the bottom? 15. And it's very much like it sets you up to do a subtraction there, right? We've got 32 above the 15, so you go 32 minus 15, and that gives you 17 neutrons. Okay? Now, there is a number on the periodic table that is going to confuse you, so I don't want you to use it in grade 9 at all. When you get to grade 11, you'll be allowed to use it. That number on the periodic table is the atomic mass. Let's go look at the atomic mass for phosphorus. Or actually, let's look at silicon here. Silicon. The atomic mass is not the mass number. Why is this not writing? Hello. Escape. There we go. This is not the mass number. It is not the protons plus neutrons. And if you look at silicon, how could it possibly be the number of protons plus neutrons? It's got a decimal. Have you ever heard of like a 0.1 of a neutron? Does that make any sense? You got like a little fraction of a neutron? It makes absolutely no sense. What that is, it is the average. It is the average of all the isotopes in nature. And you are not going to use that number in grade 9. Do not use this number. Never use this number in grade 9. Never use in grade 9. Okay? Just don't use it. Forget it's there. Pretend you've never seen it. Okay? All right. So let's just hang out with Tyler then and have him walk us through what is the difference between mass number and atomic mass, which is that number on the periodic table. So pardon me? He's going to tell us about the atomic mass. Okay? So let's go see what he has to say. There we go.
Let's talk about the difference between mass number and atomic mass. These things sound very similar, but they're actually very different. Just so you know, atomic mass can go by other names. Sometimes it's called average atomic mass, or relative atomic mass, or even atomic weight. Maybe your teacher calls it one of these. For our purposes, in this video, we're just going to call it atomic mass. So, we're talking about the difference between these two things. Let's start by talking about mass number. So up here, I've got two atoms. They've got protons and neutrons in their nucleus, and I'm particularly concerned with the number of protons and neutrons that there are. So this atom over here has 5 protons. The protons are these red circles. We can count them up. 5 protons, and the neutrons are these blue circles. We could count them up. We got 5 of those. This atom over here also has 5 protons, but it's got 6 neutrons. So, mass number is the number of protons plus the number of neutrons. So this atom here has a mass number of 10, 5 plus 5. And this atom over here has a mass number of 11, 5 plus 6. Mass number tells us how many protons and neutrons are in the nucleus of an atom. But it's also important because it gives us an idea of how much the atom weighs. You might remember, we've said before, that 1 proton or 1 neutron weighs about 1 AMU, 1 atomic mass unit. So, if you have a mass number of 10, 5 protons and 5 neutrons, your atom is going to weigh about 10 AMU. If you have a mass number of 11, that tells you that the atom here weighs about 11 AMU. These atoms both have electrons, but electrons are so tiny and they have such a small amount of mass that we don't even worry about the mass of electrons when we're weighing up stuff to determine how much the larger atom would weigh. So 10 AMU, 11 AMU. So that's mass number. Protons plus neutrons, and it gives you an idea of how much the atom weighs in AMU. Now, let's talk about atomic mass. You might notice that both of these atoms have the same number of protons in their nucleus. 5 protons here and 5 protons here. This means that they are the same element, right? Because the number of protons an atom has determines what kind of an element it is. So, we can look on the periodic table to find out what element these atoms are. And it turns out that they're boron, because boron up here has an atomic number of 5. 5 protons and your boron. So, both of these atoms are different versions of boron. They're different isotopes. An isotope is a word that just means a different version of an atom that has the same number of protons, but a different number of neutrons. We can give distinct names to these two isotopes or versions of boron. This atom over here is an example of boron 10 because it has a mass number of 10, 5 plus 5. And this atom here is an isotope of boron called boron 11. 5 plus 6 has a mass number of 11. So, there are billions and trillions and gazillions of boron atoms in the world. If we could pick one up at random, it could be either one of these two types. Okay, it could be a boron 10 atom with 5 protons and 5 neutrons, or it might be a boron 11 atom with 5 protons and 6 neutrons. So boron comes in these two versions. Now the thing is, there is not an equal number of boron 10 atoms and boron 11 atoms.
So actually, let's just go back a little teeny tiny bit. Okay, and let's get rid of the closed caption. If you take a look at that average mass, 10.8, do you think we have more boron 10s or more boron 11s? We have more boron 11s because the average is closer to 11. Okay, so we're now on page 87.
Number of boron 10 atoms and boron 11 atoms. In fact, If we pulled 50 boron atoms at random and represented them here, we'd see that the majority of the boron atoms are boron 11, which I'm indicating with little orange circles here. Okay, most of them are boron 11, and only a small minority of them are boron 10 atoms. We can look at this on a pie chart just to get this point home, and you can see that the vast majority of them are boron 11, with a smaller amount that's boron 10. If you crank through the math here, you'll find out that about 20% of the boron atoms in the world are boron 10, whereas 80% of them are boron 11. This leads us to the idea of atomic mass. Now, atomic mass asks what is the average mass of a boron atom. All right? We've got these two types of boron atoms. We've got boron 10 that weighs 10 AMU. That's what its mass is. And we've got boron 11, which weighs 11 AMU. That's what its mass is. But here's the thing. There's only 20% of this guy and 80% of this guy. So now we're asking, got these two types of boron, what is the average mass of a boron atom? Now, you might think average and say that's pretty easy. I know how to take an average. This guy weighs 10, this guy weighs 11. So why don't I just add the two of them up, 10 plus 11, and divide by 2? And then I'll get 10.5, right? That's how I take an average, okay? No, it's wrong. That is one way that you can take an average, but it won't work here.
Now, if you take chemistry 11, you'll be actually doing the calculations around this, okay? So just keeping in mind, when you go to sign up for grade 11 courses, everyone listening? If you don't like math, do not sign up for chemistry 11, okay? I'm just letting you know right now. Ms. Chatrath has a block of chemistry 11 students right now where a lot of them have not passed math 10 yet. And they are struggling in chemistry 11 because their math is really low, okay? So you don't have to be a math genius or anything to do chemistry, but you have to have decent math skills. You can't be like, oh, I barely passed math 10. I'm going to go take chemistry and that's going to work out well for me, because it won't. Okay, so just keep that in mind for next year. If you're okay at math, then you'll be good with chemistry. But if you're finding math is like a really hard subject for you, chemistry will not be your friend. Okay, so keep that in mind.
And the reason why is because this type of thing, added up and divided by 2, assumes that we have the same amount of both of these. If we had 50% boron 10 and 50% boron 11, then we could just add them up and divide by 2. But we can't do that because we have different amounts of these two types of atom, okay? And we have to come up with a mathematical equation that's more complex than this to take into account the different amounts that we have of these two atoms. Here's how we do it. We take the fact that there are 20% boron 10 atoms and that they weigh 10 AMU each, so 20% times 10 AMU. And then we add that to 80%, which is over here, times 11 AMU. And we do that math, we have to convert the percentages into decimals, but when we crank through this...
Do you guys know how to convert percentages into decimals? What is 20% as a decimal? 0.2. What is 80% as a decimal? 0.8. So when you plug it into your calculator, you would do 0.2 times 10, and then plus 0.8 times 11.
We end up with 10.8 AMU. And this tells us what the average weight of a boron atom is, taking into mind that only 20% of the boron atoms out there are boron 10, and 80% of the boron atoms out there are boron 11. Now check this out. The number that we get here, 10.8 AMU, is what's the bottom of this element name on the periodic table. So that's what this number is. It's the atomic mass that tells you what the average weight of one of these boron atoms is. Now we said we had these two different types that weigh 10 AMU or 11 AMU. Look at the average. The average is 10.8, which is much closer to 11 than it is to 10. And that makes sense, because since we have so many more of these and they weigh more, the average for these two types should end up closer to this, just because we have so many more of them. So that's how we determine what atomic mass is.
Okay, and we're going to leave it there. Okay, and the main moral of this story is that you are not going to use the atomic mass to find the number of neutrons. And we are going to go to, where is it? We're going to go to page 89. And we're going to do two examples from here, okay? We're going to do beryllium. Let's do beryllium. What is the symbol for beryllium? Go find it on your periodic table. It is Be. What is the atomic number for beryllium? It is 4. So how many protons does beryllium have? 4. Because you know what? The atomic number and the number of protons are always the same. So this little chart here is like the easiest one. Shall we try this one down here, the one with the 8? If the atomic number is 8, what else can we fill in on this periodic table? Or sorry, in this table. We can fill in the protons. The protons are also 8. Can you tell me what element is 8? Oxygen. And the symbol for oxygen is O. So that table is going to be really easy to do, okay? So we're going to skip to the next page. And we're now going to go to including now the mass number. Okay, so we now have a mass number. What is mass number equal to? It's equal to the protons plus the neutrons. And where are our protons and neutrons? They are right over here. Okay, so mass number is the protons plus the neutrons. So let's do chromium. Let's do this one here. So go find this symbol for chromium. What is the symbol for chromium? Cr. And if you have trouble finding it, remember you can always go onto the back and look up chromium alphabetically on the back of the periodic table. What is the atomic number of chromium? It is 24. Okay, and like I said, don't forget, if you can't find it, you can always be like, okay, I'm going to go to the back and I'm going to look up chromium, alphabetical order, there it is, and it is atomic number 24 and its symbol is Cr. Then we can always go to the front of the periodic table and say 24 is right there. Why is this not working? Stop. Okay. How many protons does chromium have? 24. Now this is the only one that's tricky. How do we find the number of neutrons? The number of neutrons is the mass number minus the protons. So you're going to take 52 minus 24. And if you need a calculator, feel free to borrow a calculator. 52 minus 24 is 28. Okay? Let's try this one down here. Okay, with the 32 there. We don't have any information about the element, the symbol, the mass number, the atomic number, but we are given the number of protons and we're given the number of neutrons. What else can we find? What else do we know? We know the atomic number because these two are the same. Okay, so atomic number and protons are the same, so that's 27. What else can we find out from the atomic number? We can find out the element. So let's go find our element. Number 27 is who? Number 27 is cobalt, CO. So we have cobalt. Oh. Sorry, I'm having issues with my screen today. It's doing weird things. So cobalt is CO. And now the only tricky one is the mass number. How do we find the mass number? Do we go here and say, look, cobalt is 58.9, and that says mass? Is that what we use? No. Remember, we never use that bottom number. You can just pretend that that bottom number is not there because the grade 11s use it. Okay? It's used for something else. All right? And so what do we have to do to find the mass number? Well, the mass number is the protons plus the neutrons. So it's going to be 27 plus 32, and that gives 27 plus 32 is 59. Okay. And then lastly, on our next page, the only thing we're adding in here is the number of electrons, and the number of protons and the number of electrons are the same. So that one's actually really easy. So you guys are just going to do pages 89, 90, and 91, and that's it. 89, 90, and 91. A calculator, yeah. Because that's not a mass number. Don't use that number at the bottom ever. Okay? How do you find the mass number? Would you like to Perfect. Yeah, so let's give you And there are calculators up here if you borrow one.
Oh wait, I thought I'm with I was with John. I forgot deposition. I forgot what it's called. So I said deposition. I don't know, did you have I think oh. Oh yeah, so I think the chance. Seems so good. What? Oh.
What's that? No separation versus deposition. I did the deposition, so I argued their case well.
Oh wait, isn't it different?
Do you have any plans for spring break? I am going to Ottawa and Montreal.
Really?
Yeah, with friends of mine who I've been friends with since elementary school.
Really?
Yeah.
I'm only in contact with like one of my great friends.
Yeah.
But she also goes to Mountain.
Well,
Everyone else.
back in the day,
Yeah.
if you went to an elementary school, then you all went to the then you all went to the same junior high.
Oh, yeah.
And then if you were all at the same junior high, you all went to the same senior high.
Oh.
So if you met someone in grade 4, they would be in the same school with you unless they moved until grade 12,
Oh.
right? So my one friend I met in grade 4, the other one I met in grade 7. There were supposed to be more of us going, but the other
Yeah.
ones canceled. They bailed out because of
Oh.
finances and stuff, you know.
Oh, yeah.
I mean, which is fair enough, right?
Yeah.
You know, some people had like they had to replace their driveway because it was like, you know, and the other one, her job, like they didn't have as much work for her. So
Oh,
yeah, so I get it. But it would have been nice if we could have had all of us, but oh well.
I mean, it's nice to get to go out.
It is nice to get to go out, and we're gonna go see the Parliament building
Oh,
and all that stuff. So it's kind of
I
cool.
think there's a good food there once.
Yeah, and there's really good food. So yeah, we're gonna enjoy ourselves.
Yeah. Have fun on Richmond
You
Grade.
too. Mm. You okay?
I know it's not necessarily my business, but you gotta be a bit harder than that. Literally almost a minute afterwards, you were right back to
You know what? Honestly, I got bigger fish to fry with her. She just needs to be here. And if being on her phone makes her feel more comfortable being here, then I'm like, okay, you know what? We gotta make steps. I understand where you're coming from. And in an ideal world, I absolutely would, but you know, and I've got someone who's been here like 6 days out of the whole year. I'm like, okay, let's make it happen.
Oh,
I know.
where's the fucking sword? Yo!
Nice.
It's like a katana.
You do like kendo or something like that?
Huh?
Do you do one of those? Do you do one of the martial arts with the sword? Oh, here,
Thank you so
here you
much.
go.
It's back. You're fine, you're not sick. And
Huh?
oh, you have your mask up now. Are you okay?
Oh, I'm okay. I'm just gonna blow my nose.
I was saying you finally feel better now.
You getting there?
Do we have a work block today? What?
What would you be working on?
2.1, 2.2. Oh, we could work on spring break homework.
No, that's why it's called spring break homework. That's why it's called homework.
Yeah.
Hello.
Hello.
Oh, no, fine. Fabulous.
Hi. Yeah. This is the illness that just drags on, you know? Like I feel like I'm getting like a little bit better every day, but like still hanging on there. Slow progress, yes.
Oh. Hey.
Have you ever played Portal before?
Played what?
Portal?
No.
We play Portal. It's like
Porcel?
spring break. Sorry. Yes. I hate that game.
That's
Yes, Portal.
Are
you teach you how to play?
It's like Wordle, but you try
Yeah, we have a game block.
It's like wording with horses.
the word. Yeah, basically, sure. I think it's supposed to. It's supposed to be. It's
Okay.
really play.
Have you played Game of House?
Like,
That's awesome. We should just play right now. That's awesome. That's like the best game. That's the best card.
Oh, we could have a quiz
like,
game.
Yeah. What did you think with? Honestly, I don't know the word for race practice. I just know
I'm not
evaporation.
surprised. I'm not surprised.
And I just know that.
I want to nod my head.
I got all these kids who were like,
Nod my head.
English is their first language and they don't know that going from like gas to liquid is condensation.
Oh yeah.
And I'm like, come on, guys. Like, I get it.
I also didn't know until grade 11 my country.
Yeah, I find it weird. I'm like, what do you call the stuff on your window then when it's cold in the winter? You just say there's water on it? You don't say there's condensation on it? Like, I guess they don't.
I thought you saw me there. You're gonna have if we did, I appreciate that. You know, play.
I played with it.
Have you?
I won. It was debit.
Nice.
Or like some trial.
Okay, see, we have 4, 5, we do 6. We have 6 players. That's gonna be so fun. And they're gonna work on their chemistry. Oh, Ben is also there. 7.
Yeah, 7.
Yeah, book now.
I got the color combination wrong. That's split the orange and blue. But I wasn't talking about blue. That's why I'm oh,
Sorry, I have to tell you, I've got to leave early today.
Okay,
I've got to go home, pack up, and go to YVR. Sky Gym there
okay.
for a vacation.
Where are you going?
Okanagan.
Nice.
I want to check out the UBCO
Oh,
campus.
yeah. Very good.
I hope you have a great vacation too.
Yeah, you too.
Thank you.
Cool. Okay.
I'll never eat.
Nothing, genuinely, like, what is everything sometimes?
Why?
All friends. Good. One. We need to love it.
yeah, like yesterday. And then
Mine's
I
like-
found out. Big trip.
I don't want to say.
So funny because all those idiots. Probably got ChatGPT.
Okay.
No,
Yeah. Why are we jumping? Oh.
Huh?
Why are we jumping to the end of the
Because you guys are doing 4.1 over the break.
bro, we had.
Did you not get the?
Yeah, but I think those are just practice.
These are what?
I thought those are practices.
Practices?
Practice. Just like.
That you're learning it. There's videos. You'll watch them and learn words and learn concepts. Okay. But it's not hard. It's easy. It's, you know what, honestly, it's free marks. If you put your mind to it, you could do it in like a half a day.
Do it on the first day.
You could be like, I'm just going to do it tomorrow morning. Do it today. Go home and do it after school today.
I have puppy games today.
Doesn't matter. Do it while you're playing hockey. Yes, but this is page 73.
What? Oh, not 83, 73. Not 83, 73. My brain. Oh dear.
It's alright. It's fine.
Yeah. What? We are. We're going to work all class. Watch me go. Okay. So,
Heavy cheese. cheap.
The logarithm, you know what? The faster I go, the faster we're done. So if you all want to talk about how you're sad that we're working today, you can do that, and we'll just be here till 3. Or we can go quickly.
Okay, let's do it.
Okay, good. So the logarithm of 1 times 10 to the negative 5 is negative 5.0. Why 0.0? Because sig figs. Because what is this negative? Hang on. I need this over here so that I can press escape. Oh my God. Okay. Okay. So the logarithm of 1 times 10 to the negative 5 is 5. Negative 5, sorry. Where did that negative 5 come from? That came from the power of 10. So that is not a significant figure. Okay? How many sig figs are in 1 times 10 to the negative 5? 1. So we need to have then 1 sig fig. In your head, can you do this? Log of 10 to the negative 3. It's just negative 3. Okay, that's how logs work. So what is the log of 10 to the 7? 7. And what is the log of 1 times 10 to the 4? 4.0. Because we have our 1 sig fig and our 1 sig fig. Now, if we have something else instead of just a 1 in front of the power of 10, if we have a different coefficient, could you please chuck that into your calculator and tell me what you get? What do we get? Negative 4.3. Okay. Now, do we have the correct number of sig figs there? Yes. 1 sig fig. 1 sig fig. Now, chemists thought, let's just, instead of writing all this 5 times 10 to the negative 5, let's make pH. And so we'll just write it as a number. And so we took the log, and then they were like, this is a pretty good system. But then they thought, most of our concentrations are fractional, like 0.1 molar, 0.05 molar, things like that. So all of our exponents are going to be negative. So all our pHs are going to be negative. So let's then change that to a positive value by taking the negative of the log. Okay, so pH is defined as negative log of, Oh, sorry about that. Log of 5 times 10 to the negative 5 is negative 4.3 because 5 times 10 to the negative 5 can actually be written as 10 to the negative 4.3. Those two are equal. Okay, so if you raise 10 to the negative 4.3, you will get 5 to the negative 5. All right, so we have log of H plus, and we are going to learn a new ion today, and that ion is H3O plus. H3O plus is called the hydronium ion. And the hydronium ion is it's how hydrogen actually exists in water. So when we write H+, that's actually like a shortcut. Okay, not reality. H3O+, that is reality. So if we were to take, for example, hydrochloric acid, HCl, and we put it into water, instead of just dissociating into H+ and Cl-, we are actually going to have this hydrogen here is going to detach from the HCl, and it's going to attach to the water. And what we will end up with then is Cl- and H3O+. So H+ and H3O+ really mean the same thing, okay? This one's just the shortcut. Shortcut. This one is reality. So we could also write that pH is the negative of the log of H3O+, the hydronium ion. So we are told that hydronium ion is equal to 3.0 times 10 to the negative 3, and we can then calculate the pH. When you're doing this, you should write the formula. Okay, so you're going to write pH equals negative log. And in this case, we have been given an H3O+ value. So let's use the H3O+ version of this formula. And then you're going to plug in your number. So negative log of 3.0 times 10 to negative 3. And we don't need a unit because pH has no unit. And what do you get? 2.5? We get, well, I'm going to write the whole thing down. I'm going to say we get 2.5229. All right. Now, what should we round that to? 2.5? Now, how many sig figs here? 2 sig figs. And this number has been logged. And remember, when we have a number that has been logged, we only count digits after the decimal, okay? Therefore, only digits after the decimal are significant. Okay, so not just 2.5, but it's going to be 2.52. Okay, so that has 2 sig figs. So numbers in front of the decimal indicate what the power of 10 we're talking about, and they are not counted as sig figs. So only digits after the decimal are significant in a logarithmic number. Okay, so you're going to practice doing this and showing all of your work and correct sig figs. Go for it. Do it as quick as you can. If you need to borrow a calculator, there are many calculators over there. And I'm going to go grab 2 more. Anyone need a calculator? Oh, so what you do is you type in your thing, and then you press log. Type in your number, and then press log. Oh, exponent. Yeah, exp down at the bottom. No problem. Now, one thing I'd like you to notice here is that the coefficients in both of these numbers are the same, and the numbers after the decimal are the same, because it is the number after the decimal that represents what's going on in the coefficient. Okay? It's really only the power of 10 that's changing, and that's the number in front of the decimal that's changing. How many sig figs should we have here? 2. So that's going to become 11.27, and that's going to become 6.27. What should our number be for this third one? It should be negative 1.176, because we have 3 sig figs here, and we have 3 sig figs here. And I threw this one in here because I wanted you to see that yes, pH can be negative. But you have to have quite a high concentration, like 15 molar is very concentrated. By the way, is there anyone in here who did not get the spring break assignment? Everyone got it? Cool. Okay. And this last one I threw in here, well, number one, because again, we have two sig figs, to prove to you that pH can be greater than 14. But, I mean, if you look at the concentration, 10 to the negative 17, that's tiny, right? So pH can be greater than 14. Oh, you would just have to, like, you would have to have a very high concentration of hydroxide, which would drop the concentration of hydronium very much. All right, are we good with that? Okay, auto. The prefix auto means self. So if you have an automatic car, it drives itself. Okay? Ionization means turning into ions. So water actually does, on its own, turn into ions. It doesn't do it very much, only a very, very small percentage does. Okay? And our shorthand method, you guys don't know what shorthand is, but that's okay. You can say shortcut. Go look up what shorthand is. It's this like little series of squiggles and stuff that they used to use when, back before there was speech to text, people would, like the big CEO in the company, they would like dictate to the secretary, and the secretary would take notes in shorthand, which was like, it's faster than writing, like words, because they have things for syllables and words, single symbols. So they would learn that, and then they would take the shorthand and they would transcribe it and then type it up into a letter, and then they would send the letter off. It is its own language, yeah. And people used to go to school and train for it. Yeah. And then that became like obsolete. Yeah. Anyway, that was shorthand. So shortcut method is we just take H2O, and what would it turn into as ions? H plus and OH minus. So this one is water is what state? Liquid, and those two are aqueous. Okay. Now, in reality, this is not what happens. In reality, we have one H2O molecule, and it gets together with a second H2O molecule. And one of the hydrogens from here moves over and attaches to the other hydrogen. What would that first water molecule turn into with that extra hydrogen? H3O plus, the hydronium ion. What is left after water gives up a proton? OH negative. I said proton. We haven't gotten there yet. We need to talk about that.
Why does water do that?
Why does water do that? Because it just does.
Why can't H plus exist by itself? Why does it have to exist as H3?
Because it's more stable. Everything is to do with stability and randomness. Everything. Okay? Now, in this equation, we're going to learn a new word here. In this in reality equation, we have water acting as a, and here's our new word, Bronsted-Lowry, those are two scientists, acid. Okay? A Bronsted-Lowry acid is a substance that donates an H plus to another species. So we have a Bronsted-Lowry acid. It donates hydrogen. Out of those two waters, is the first water or the second water a Bronsted-Lowry acid? Who is the Bronsted-Lowry acid according to our little diagram there? The second one. So that's our Bronsted-Lowry acid. Okay. Now, the other water is called a Bronsted-Lowry base. And if you want to get really fancy, you can put the umlaut on the O. Umlaut. You don't have to. Now, our Bronsted-Lowry base, it is a substance that does what? That, I'm going to use the word accepts because that's the one that gets used mostly. H plus from a Bronsted-Lowry acid. So who's acting as the Bronsted-Lowry base? That would be our first water. Is it always true what? No, I just picked one. I picked it so that I could have the H3O plus go first in my products because usually we go H plus and OH minus, and it makes more sense for it to be analogous with the H3O plus and then OH minus.
Oh, that's random, right?
It's random, yeah. I mean, quite frankly, we could have written this one, don't do this, but you could have written this one as OH minus plus H plus, right? But it looks ugly. And the same thing for this one down here, it would have looked ugly. Yeah, but it is random, totally random, doesn't matter. Now, we need to learn a few other words here. So, first of all, we are going to talk about the hydrogen atom. How many protons? How many neutrons? And how many electrons are in a hydrogen atom? There's one proton. How do you know that?
I counted.
You counted. All right.
It's on the table.
It's on the table. Okay, so if we go to our periodic table and we go look here, right, there's a 1.
Right.
Okay, and that's our atomic number, right? What does our atomic number tell us? That tells us our protons. Now, an average, An average hydrogen atom average mass is 1. So how many neutrons does that mean we have? It means we have 0 because remember, protons have a mass of 1, neutrons have a mass of 1, and electrons are essentially mass of 0. Close enough that we just ignore them. Okay, so if we've only got a mass of 1, then we only have 1 proton, and we have no neutrons because otherwise the mass would be 2 or 3. Okay? So we have 0 neutrons. And how many electrons in a hydrogen atom? 1, because atoms are neutral. So we have to have the same number of positives as negatives. And if we were to draw this, here in the nucleus is our 1 proton, and around the outside is our 1 electron. Now let's find an H plus ion. How many protons, how many neutrons, how many electrons? There's 1 proton. How many neutrons? None. How many electrons? None, because our charge is +1, so we only have the 1 positive. We don't have any negative canceling out that charge. So if we were to draw that, what would it be? It's just that. And what is that? That is a proton. So very often we will just call hydrogen ions protons. Okay? Therefore, we call H plus ions protons. It doesn't need them. Neutrons they're kind of just there to glue the protons together, because 1 proton and a second proton will repel one another, yes? And you end up with the neutrons. I don't really understand it, but they provide the strong nuclear force, whatever the heck that is. And they glue the protons together, essentially. Because there's only 1 proton, no glue is necessary. So,
they repel.
well, protons repel each other,
Yeah.
but there's only 1 proton. So it's not repelling anything. Yeah? Right? If you go to, say, helium, now you have 2 protons. Those are going to repel each other, and so that's why you need the 2 neutrons that generally go in there. Okay? All right. So we call hydrogen ions protons. So now we're going to think about the word both. Both. Now, if you think about a frog can breathe both air and in the water. It gets oxygen from both the air and from the water. It can live both on land and in the water. What do we call the types of animals that can live both on land and in water? You guys don't know? What kind of animals are frogs? And salamanders? Amphibians. Amphibians. Both is the prefix amphi.
Ambidextrous.
Kind of, yeah. Amphi and ambi, they're sort of like the same root. Ambidextrous means you can use both your left and your right hand. So amphi. Protic means to do with protons. To do with protons. So now let's remember, a Bronsted-Lowry acid donates H+, which is a proton, to another species, and water also accepts protons, a proton, from a Bronsted-Lowry acid. So water can do both. It can donate a proton and it can accept a proton. It does both. Therefore, we say that water is amphi, both, protic. Okay? Amphiprotic. Because it can do both things with protons. It can donate them and it can accept them. Not all species are amphiprotic. Acids like HCl can only donate protons.
Is water the only substance that I would?
No, there are many. Okay? We'll come across more of them later. Now, what you guys are going to do next is you are going to take these two equations here, this one and this one, and you are going to write the KEQ expression for that one and that one. So write the KEQ expression for the autoionization of water in the two ways from those two equations.
Wait, does it have to be the same type of liquid? I forgot. Like the exception to.
Well, if you have water and you have water, are they going to dilute one another? It's just 2H2O. You could write it as 2H2O instead. Okay? So no, there's no water cannot dilute water. Okay? So what is KEQ for the first one? H plus times OH minus. And for our second one, KEQ is H3O plus times OH minus. And we could put divide by 1, but we're not going to because that just complicates matters. Yes? Now, do you guys remember what we call the KEQ for water? We call it KW. PKW. Okay, so we have two ways of writing KW. Do you guys remember what the value of KW is? What the number is? Yes, KW is 1.0 times 10 to the negative 14. And that's at 25 degrees Celsius. Now, would it change if we put it at a different temperature?
Yeah.
Yes, because K's change when we change the temperature. You can assume that unless I say otherwise, you are always at 25 degrees Celsius, okay? So if I don't say anything different, you're at 25 degrees Celsius. Now, if you forget that number, where can you go find it? Page 6 of the data booklet. You can go and look and you're like, okay, it is right down at the bottom of the white section there. 1 times 10 to the negative 14. Okay. So we have one equation and 3 variables. 1, 2, 3 variables. So if I give you 2 of those variables, can you find the third? Yes. So for example, we can use hydrogen or hydronium and KW to find hydroxide. In this instance, we are given hydronium. So which version of the Kw expression would we use? H3O plus times OH minus. And then our other blank over here is to give the value of Kw. What is the value of Kw? 1.0 times 10 to the negative 14. 2 sig figs there, by the way. Okay. And now we're going to find concentration of hydroxide. Can you solve this equation here for hydroxide? Yes. Hydroxide is equal to what? Kw divided by concentration of H3O plus. And then you just plug in your numbers and solve. What do you guys think of my answer?
Sig figs.
Sig figs. You cannot leave that little repeater there. Okay, I'm just going to get rid of it because it'll round to the same thing anyway. Okay? What do you think of my answer now?
Sig fig. Oh, yeah, 2 sig figs.
2 sig figs. Do I have 2 sig figs?
You do.
I do. I have 2 sig figs. 2 sig figs. Yay! And I forgot my unit because it is concentration. So that is molarity. Okay? And we're done then.
Yes.
Okay? So that's full marks. You've shown your formula. You've shown the plugging in. You've got your answer to correct sig figs with the unit if there is a unit needed. Okay? Since pH equals negative what? pH equals negative log of H plus or H3O plus. Then it must be that pH equals negative log of OH minus. So let us now then find the pH and the pOH for that example we did back there. Remember, we had our hydrogen ion concentration was 10 to the negative 3, and our hydronium ion, or sorry, our hydroxide ion concentration was 3.3 times 10 to the negative 12. So let's find our pH and our pOH. We've given you the numbers again. Okay. So show your work, do the calculation. All right, what do we think? Sig figs. So this first one should be 2 point what? 52. 2 sig figs. 2 sig figs.
Yeah. 11.
11. Okay, and our next one is going to become 11.48. No.
What are you talking about? What are you talking about?
All right. Examples. Find the concentration of hydroxide and the pOH of the following solutions. So we're going to be finding concentration of hydroxide and pOH. And so make sure that you have your work written this way. So you're going to show Kw, all right? You're going to show solving that for hydroxide. The only one you don't really need to show is this one, but for now it's kind of useful because it'll remind you what the value is. Okay, and then you're going to show your plugging in, and then you're going to show your answer. Now, is that the correct answer for hydroxide concentration? No, what's wrong with it? We need sig figs, so that's going to become 0.0019. Anything else? M. You could put it in scientific notation. There's only 2 zeros, so I would say it's optional. Sort of when you get into the 3 zeros, it starts to get a little dodgy. Okay. Now, our second part of the question is finding the pOH. So that's our negative log. So show our formula. Negative log of hydroxide. And then plug in our number. Now, question. Would it be okay? Is negative log of 0.0019 okay?
No.
Like if instead of writing 0.001851, would it be okay if I wrote 0.0019 instead and did that in my calculator as 0.0019?
No.
No. Okay? And why is that? Because if we take the negative log of 0.0019, 0.0019 log, we get 2.72124, which would then round to 2.72, which is a rounding error, yes? Because what should we have gotten if we didn't round it? We got 2.73 as our pOH, okay? So don't round off your digits, just keep the entire number in your calculator, press log, and Bob's your uncle. Have you guys heard that expression?
Yes.
It just means, and there you go. Okay, try the next one on your own. Yes, I'll come back.
Here's my word.
Yeah, I did it with the spoken.
You didn't do it today?
Yeah, so this
I'm so excited.
scientific development in history.
Oh my god.
Yes.
So that's all.
Yes.
We can all.
Yes.
You know what Indian people like oil up their hair?
What?
So what if we do that? What if we talk? What if we do that with stimulus?
After that, you can
Wow. So abstract.
Oh yeah, Justin. Here.
I would be such a good graffiti artist. I would do vandalism so well.
He's not.
I give up my umbrella.
Question. Is this number here going to be 1.8 or sorry, 1.9 or 1.85? Is that number there going to round to 1.9 or 1.85?
One. Huh? I helped Justin.
Like for sig figs or for calculating?
For sig figs.
That's it, you guys work well?
Is that wrong?
1.9.
1.85. Oh no, 1.9.
No,
Is this a logged number or a non-logged number?
Not long. 1.8.
Non-logged.
1.9.
So it should be 1.9
Yeah, 1.9.
times 10 to the negative 8.
It should be enough for the 1.9.
Yeah.
We don't need to round it up.
Yeah.
Okay.
I said wrong.
And don't forget, what else did I forget here? Molar.
Hold up. So what guy? Well,
Now,
Justin,
I
how old-
wrote 1.9 times 10 to the negative 8
How old is that?
in my calculator. Do I have 1.9 times 10 to the negative 8? No, I have 1.851851,852. And I just press log, and there it is. Sorry. And what should that become? 7.73. Yay. Okay. Now, question. We have another example that is exactly the same work. Do you want to do one more example?
No.
No.
Okay, moving on. Okay.
Thank you.
You're welcome.
So we know that pH is negative log of hydrogen, and we know that POH is negative log of hydroxide. What do we call it if we take the negative log of Kw?
Justin.
What do we call it if we take the negative log of Kw?
Justin.
We call it Justin? What?
Somebody's serious.
Or maybe not.
Maybe not.
Maybe not. What do we call it? pKw. Okay, so there we go. Log of Kw, negative log of Kw is equal to pKw. And we can actually do that math, okay, at 25 degrees Celsius. Kw is 1.0 times 10 to the negative 14.
I gave it to him.
So let's play with these numbers a little bit here. If we have concentration of hydronium is 1 times 10 to the negative 5. What is the concentration of hydroxide? Yeah, which is 1 times 10 to the negative 9. Yes. Okay. Now, you can do it in your head because they are just powers of 10 that you're playing with, but you could also do the work here. You could be like, okay, that's 1 times 10 to the negative 14 divided by 1 times 10 to the negative 5 gives 1 times 10 to the negative 9. What are the pH and pOH? Can you do that in your head? If we have hydrogen ion, what is the pH? pH is?
No, 5.00. Yeah.
Because the coefficient is 1, you just look at the power of 10, and so it's going to be a 5, right? Because that's our 5 there. And it shouldn't just be 5, though. It should be 5.00. If you don't feel comfortable doing that in your head, please feel free to plug it into your calculator. But if you've got a coefficient of 1, you can just do it in your head. What is the pOH? This is our hydroxide ion concentration. What is the pOH?
It's 9.00.
9.00, because we've got our 9 there,
Oh, yeah.
and that becomes a 9. Okay, so we have pH is 5, pOH is 9. What do we get if we add those two together?
14.
We get 14. If we add pH and pOH together, we get 14. Why?
Because pH plus pOH equals 14. That's the law.
Exactly. Okay, but we're going to do like a little math. Okay. We're going to do the math. You are not responsible for being able to do this derivation. However, it's pretty straightforward, and it is an application of your math. It is an application of very easy log math, okay? So let's take our KW expression. We are going to log both sides. In fact, we're going to negative log both sides. So we're going to negative log the left side, and we're going to negative log the right side. Now what we have here is we have negative log of A times B. Yes? So we have an A, and we have a B. And if you remember your log rules, what is the log of A times B?
Log A plus log B.
Log A plus log B. So we're going to apply that log rule. Shiho, could you close the door for us, please? Thank you so much.
What's wrong with Justin?
So we still have that negative there, so we're going to keep the negative around. Okay, so the negative's just hanging out here, and it's hanging out here. All right, but we're adding now. We've got negative log, we've got the negative log of hydrogen plus the negative log of hydroxide. Now, what is negative log of hydrogen? Negative log of hydrogen is pH. What is negative log of hydroxide? pOH. And what is negative log of KW? pKW. And KW is 1 times 10 to the negative 14. pKW is the negative log of KW, so it is the negative log of 1 times 10 to the negative 14, which is 14.00. So at 25 degrees Celsius, you don't need to be able to do any of that stuff with the logs, but it's just there because it's interesting. Okay, at 25 degrees Celsius, 14 is pKw, and both of those things are equal to pH plus pOH. Now, if you're not at 25 degrees Celsius, then the value will change from 14. Okay, we'll look at that later, but for now, that will do. Now, Hebden has a lovely little chart on page 138, but I've copied it here so you don't have to go rooting around in Hebden to find it. And we're going to look at just the very tippy top of that chart right now. And we have hydronium, which could also be hydrogen. Why does it do this to me? Why? Okay, here we go. Okay, H3O plus. If we want to go from H3O plus to hydroxide, we use Kw. And what is Kw? Kw is 1.0 times 10 to the negative 14. And that relates hydronium and hydroxide. So we can go back and forth between those two very easily using that formula. Let's go to the bottom of the chart now. Now we have pH and we have pOH. All right? How do those two relate? They add up to 14. pH plus pOH adds up to pKw, and pKw is 14.00. All right, so that gets us from left to right, hydronium to hydroxide, hydrogen, pOH to pH. Now we're going to go up and down. So if we want to go from hydrogen or hydronium to pH, pH is equal to the negative log of hydronium. Okay, or hydrogen. How do we go the other way? How do we go up? Magic. So if we want to find the concentration of hydronium, it is 10 to the power of negative pH. Okay. And on our other side, pOH is equal to the negative log of OH. So that takes us from the top to the bottom, OH to pOH. What if we had pOH and we wanted to find hydroxide? What would that equal? 10 to the negative pOH. And that would take us back up. Should you memorize this little chart? Yes. Okay. Well worth your effort. At some point, you won't need to use a chart. You'll just know them all, but the chart is very helpful for when you're first starting out. Okay? So know this chart. Now, just as a reminder, if you're confused and you're like, I can't remember how to do the pH to hydrogen, if you remember, when we find a pH, first thing we do is we log the hydrogen, and then we change its sign. So to go backwards from pH to the opposite, we're going to first change the sign, and then we're going to do the opposite of log, which is anti-log. Okay, and anti-log just means 10 to the x. Okay, but you should be familiar with the word anti-log because it is, well, you should know what it is, because if you come across it and you're like, I've never heard of this thing before in my life, what does it mean? Well, then you're kind of like hooped, right? Whereas if you know that anti-log is 10 to the x, then you're good to go. It just means the opposite function of a log. Just like the opposite function of squaring is square rooting. Yes? Anti-square rooting. Anti-squaring. Okay. So you could write the equation like this if you wanted to. You could say hydrogen ion concentration is equal to the anti-log of the negative of pH. Or you could write it as 10 to the negative pH. They both mean the same thing. Now, if we have a pH of 4.0, we take hydrogen ion concentration, that's 10 to the negative pH, so that's 10 to the negative 4.0. How many sig figs here? Are there 2 or 1? Is pH a logged number? pH is a logged quantity because you took the negative log to get pH. pH is a logged number. Okay, so how many sig figs? We have 1 sig fig. So when we go to our final answer then, we say we have 1 sig fig here. And now we're in an unlogged number. So we're going to have 1 sig fig here. Okay, so it's pretty straightforward. You just use a button on your calculator. The only thing that can confuse you is the sig figs. Remember, any p number, any p value has been logged. Yeah. So any p value, that would be like pH, POH, pKw. And therefore sig figs are after the decimal. Is good? Okay. Good Lord. Oh my God. I can't wait till my voice is back. We're almost done. Okay? Recall, in pH, only digits after the decimal are significant. So therefore our answer must also have 1 sig fig. Now, what if we have a pH of equal to negative 1.00? We have here, how many sig figs? 2 sig figs. Because that's a p value. It's been logged. So our final answer is going to be, if we take 10 to the negative 1, we'd get 10. Does this number have 2 sig figs? This has only 1 sig fig. How can we write it so it has 2 sig figs? We can write it as 10 decimal molar, that has 2 sig figs, or 1.0 times 10 to the 1 molar. Either of those are acceptable answers. Okay. And last one, and then we're done, and we're done like 10 minutes early. Look at us go. Okay, 7.320, if we take the anti-log of that, which remember is just 10 to the negative 7.320, what do we get? Throw that in your calculator. We get 4.78630009. Okay, times 10 to the negative 8. What should that be? 4.9? What? 4.7? 4.8? Hold on. 4.7? 4.8? How many digits should we have? We should have 3 digits, right? Because we're now back into molarity, which is not logged. So we want 4.79. That's 3 sig figs times 10 to the negative 8 molar. Okay, and we're done. And your homework is your spring break homework. Everyone has a copy. Yes? And you are absolutely required to stay here for the next 10 minutes. But just remember that if you were to, like, go to the washroom and you went and wandered down near the office or made noise in the commons, your teacher could get in huge trouble. Do we understand each other? Excellent. You may go to the bathroom. Sorry about that. Have a great spring break. You can never use your phone in class. You can go to the washroom and use it.
Let's do the old fashioned. How's the weather today?
What did I just say?
Can I go to the washroom with my bag?
You may go to the washroom with your bag. And if any administrator sees you, whose class are you in?
Mr. Weinberg.
Mr. Weinberg. He's retiring. He can't get in any trouble.
I don't think he can like get in trouble even if he wasn't.
I don't think he could either.
Grade 8.
Honestly, no one would believe it was him.
Grade 8.
Huh?
Like,
And stack chairs in the corners of the classroom before they leave.
No, we're not doing that.
oh my god, I thought it was
These don't stack.
And stack chairs in the classroom before you leave. Thank you.
I thought they were going to be like, don't let those students out.
They all went to the washroom. I was in a metaphysical center.
My brother was there, so basically.
My spirit was there. My soul was with you. Kate, I'll see. Whatever makes you feel better.
Okay, Mom, I'm speaking. That's a good day for you.
Yeah,
You don't need to take.
yeah, that would say some gas.
When are you going to?
I'm leaving at 8:10 tomorrow morning, which means I need to leave my house at 5:20 a.m.
I'll be fine.
Put your bag just beside the window.
I seem like what?
Like you finished packing with 5 days and
No, I just finished packing yesterday because
Jesus, man.
there was so
I
many
would
other
suggest
things
you
on
don't
my plate,
go.
plus the illness.
I would
It ate up a whole
Yeah.
bunch of time that I just
He never ending. I am still
Mine
sick.
is great. Like it seems to go away.
What
Like,
room do I?
Hi.
What should we do with our chairs?
I'm not doing
they're
anything.
unstackable. Just
I'm
leave
not
them where
doing
they are.
anything with my chairs. I'm just gonna leave
Yeah,
them.
because they're not stackable.
They don't stack.
And if they're gonna take them off the desk anyway, so we put them up there.
Yeah, I'm not gonna worry about it.
And I just lost it. Very simple. Something like.
What? Yes.
It's the best. I suggest you don't go white. Because he's gonna be the pilot because he wants like to come with you on the boat. So that's the time that makes.
I just practiced that part because I didn't think I was on it. I was like, yeah, we're gonna do up there. And that was so cool.
You too. Hello. Class is done. No. What did you figure out? Yes. Oh. What is it?
Ethan what? Him.
Oh. Okay. That's hilarious.
That was so unfortunate. His spring break. It's like they each went 2 years ago.
Yes.
What did you even do?
Oh my god, that's so funny. Oh my god, that's so hilarious. Yeah, I know. Like,
I'll have you know that I was ballistic for Amy, and then she won. And I got
yeah. Have a good spring break. Sorry, no, it's okay. They're just leaving the room. So, yeah.
But I'll see a date though.
Oh my gosh. That is amazing. That is hilarious. Oh, I should let you know. I'm going to be in Ottawa, Montreal for the next week. So I may not be phoning you at 8:30 because that'll be like 11:30. Have a good spring break. And we'll be out doing things like visiting parliament buildings or whatever. So if you need Candy and Devlin and Will and Allegra. Yeah. So if you need anything, you can call me, but I won't call you because I'll probably be out and about and doing things. Does that sound like a plan? Yeah, because I'm never going to remember to do it. And plus I'll be out with friends. And, yeah. And I don't want to phone you at 8:30 that time because then that would be like 5:30 a.m. That would suck. Okay, I will do. I love you, kiddo. Bye. How's my son? We have these exercise videos we do, and there's this one song where the lyrics, we didn't know what the song was called, and the lyrics literally sound like the person is singing testicles. It goes, testicles, testicles. And we're like, surely that is not what it actually is. Like, what is it? It turns out it's called Tesla Girls.
Oh, wow, let's listen to it right now. Actually, that's
But we couldn't figure it out for the longest time. And I've had these videos since like 1995. And for all of that time,
Tesla wasn't big back then.
no, it was like from Nikola Tesla.
Oh.
Okay, yeah.
The child back then.
So like, but it was so funny because like, I told him and I'm like,
That's so 1995.
isn't it?
Let's see when this.
It's a good workout song.
1988.
That's so
To take my test. I mean, sorry, my quiz yesterday. Oh.
It's gonna come for flex.
Do you want to like take it home as a practice quiz over the break?
Sure.
Okay.
Can I get another quiz when I come back?
No, you can just do it as practice. Does that sound okay? You happy with that? Okay.
Thank you.
Let's find that for you.
Why is it singing?
There we go. And I'll give you an answer key.
Yeah.
Okay. Which I have here somewhere.
Oh my god, it does sound like that.
Where have I put them? That's the big question.
Okay. I can hear it.
Does it not sound like I swear to God?
You look so warm. I'm gonna put you at either. You got that feeling you look way off.
You think it's so sad? Always upset for good reason.
You don't have Eastern European sorrow inside.
What the hell?
I think it was good.
Thank you. Have a good break. Bye.